Dr. Neelu Dheer from Acharya Narendra Dev College, Delhi University. The topic of my series today is conductance. Let us begin with the experiment number 2. The aim of the experiment is to determine the molar and equivalent conductivity of 0.1 normal acetic acid at room temperature. In our previous experiment, we had determined the cell constant. The materials required are conductivity meter, conductivity cell, 100 ml beaker, standard flask, pipette, acetic acid and deionized water. The stock solution used is 1 normal acetic acid solution. Dilute the stock solution to prepare 100 ml of exactly 0.1 normal acetic acid solution using the formula N1V1 is equal to N2V2. The volume of the stock solution, that is 1 normal acetic acid solution, that is to be taken to prepare 0.1 normal solution in 100 ml comes out to be 10 ml. So take 10 ml of 1 normal solution in the measuring flask and make up to 100 ml using the distilled water. Take 40 ml of this 0.1 normal acetic acid solution in a 100 ml beaker. Measure its conductance using a conductivity cell of known cell constant. Dilute the 0.1 normal acetic acid solution to get solutions of the concentrations 0.05 normal, 0.025 normal, 0.0125 normal and 0.01 normal according to the given table. Dilution of 0.1 normal acetic acid solution that needs to be done is according to this table. Take 0.1 normal acetic acid solution 20 ml, add 20 ml of water to make 0.05 normal acetic acid solution. Similarly, the other dilutions can be done to prepare 0.025 normal, 0.0125 normal and 0.010 normal acetic acid solution. Take 40 ml of the stock of 0.1 normal solution in 100 ml beaker. Measure the conductance using the same conductivity cell. Repeat this for all the above solutions which we have prepared. Calculate conductivity and equivalent conductivity of each solution. The molar and equivalent conductivities of acetic acid are equal. Observations to be made are: room temperature is to be noted, cell constant from the previous experiment number 1 has to be noted. Observations in calculation: the conductance measured should be tabulated, the conductivity kappa is G into cell constant and equivalent conductivity lambda C can be calculated, which is equal to 1000 kappa by C. Result: the values of molar and equivalent conductance of acetic acid as calculated for different concentrations are to be noted according to this table. Precautions: use clean and dry beaker for each solution. Rinse and dry the conductivity cell before measuring conductance of a solution. Dilution should be done accurately. Effect of dilution on specific conductance: when an electrolytic solution is diluted, number of ions, that is the current carrier present per unit volume, decreases. Since specific conductance is the conductance of a centimeter cube of a solution, it is expected that its value falls with dilution. Thus, the conductivity or specific conductance increases with the increase in concentration. Effect of dilution on equivalent and molar conductance: the value of equivalent or molar conductivity of both strong and weak electrolytes increases on dilution. Lambda equivalent or lambda molar is equal to kappa by C. The value of kappa decreases with dilution because number of ions per unit volume of solution decreases. The increasing factor 1 by C is much greater than the decreasing factor kappa. Thus, the equivalent and the molar conductivity increases on dilution. The variation of equivalent conductivity with concentration is plotted and shown in the graph lambda versus under the root C for the strong and the weak electrolyte. For strong electrolytes, we can see that the variation is almost linear in dilute solutions. They have high value of molar conductivity even at low dilutions. There is no rapid increase in the value of lambda on dilution. There is a tendency for molar conductivity to approach a limiting value when the concentration approaches zero. This stage is called infinite dilution. The equivalent and molar conductivities have a limiting value at infinite dilution and are represented as lambda equivalent infinity. It can also be represented as lambda naught m or lambda naught equivalent. For weak electrolytes like acetic acid, they have low values of molar and equivalent conductivity at high concentration. There is a rapid increase in the value of lambda m or lambda equivalent with dilution. There is no indication that a limiting value of equivalent conductivity can be obtained even when the concentration approaches zero. Thus, graphically, lambda naught of such electrolytes cannot be obtained. Theories of weak and strong electrolytes. Theory of weak electrolyte. Ostwald gave the theory of weak electrolytes on the basis of Arrhenius' theory of electrolytic dissociation. According to Arrhenius' theory of electrolytic dissociation, there exists an equilibrium between the undissociated molecule AB and the ions A plus and B minus, which results from the dissociation of the molecule. Thus, AB is in equilibrium with A plus B minus, and the K equilibrium for this dissociation, this equilibrium is equal to A plus into B minus by AB concentrations. If alpha is the degree of dissociation and if C is the initial concentration of the electrolyte AB, then the concentrations of A plus and B minus can be written as C alpha, and the concentration of AB is C into 1 minus alpha. Substituting these, we get K equilibrium is equal to C alpha into C alpha by C into 1 minus alpha, or C alpha square by 1 minus alpha. Since for weak electrolytes, alpha is much less than 1, we can neglect alpha in comparison to 1 in the denominator, and we get K equilibrium is equal to C alpha square, or alpha is equal to under the root K by C. The expression alpha is equal to under the root K by C is known as the Ostwald's dilution law, according to which the degree of dissociation increases as C decreases. As alpha is increased, the concentration of A plus and B minus is also increased. Thus, the increase in conductivity, both equivalent and molar, for a weak electrolyte is primarily due to the increase in the number of ions on dilution. Degree of dissociation alpha is equal to lambda C by lambda naught. It can be calculated using this expression, where lambda C is the molar conductivity of the solution at the given concentration and lambda naught is that at infinite dilution. Substituting this expression in the equation number A, K equilibrium can be written as C into lambda C by lambda naught whole square divided by 1 minus lambda C by lambda naught. Determination of the ionization constant of acetic acid, we can use this equation K equilibrium is equal to C into lambda C by lambda naught whole square divided by 1 minus lambda c by lambda naught. Reciprocating this equation, we can get 1 by k equilibrium is equal to 1 minus lambda c by lambda naught divided by c into lambda c by lambda naught whole square. When we rearrange, we get c lambda c whole square by k equilibrium lambda naught square is equal to 1 minus lambda c by lambda naught. Dividing throughout by lambda c and rearranging, we get 1 by lambda c is equal to 1 by lambda naught plus c lambda c by k equilibrium lambda naught square. If we plot 1 by lambda c against c lambda c, we will get a straight line with slope equal to 1 by k equilibrium into lambda naught square and intercept equal to 1 by lambda naught. So, k equilibrium can be calculated as 1 divided by slope into lambda naught square. And from the equation number 2 of the intercept, lambda naught square will be equal to 1 by intercept square, and thus k equilibrium or Ka becomes equal to intercept whole square divided by slope. For strong electrolytes, we have Debye-Huckel-Onsager theory, according to which strong electrolytes are known to be completely ionized in solution. The increase of equivalent conductivity on dilution cannot be ascribed to a change in the number of ions, as this is constant for 1 gram equivalent of the electrolyte at all concentrations. The falling of lambda equivalent with increasing concentration must be due to the decrease in the ionic velocity. This is the basis of inter-ionic attraction theory of Debye-Huckel-Onsager. According to this theory, each ion in solution is surrounded by an ionic atmosphere consisting of other ions whose net charge is opposite to that of the central ion. This ionic atmosphere is spherical and symmetrical in nature in the absence of any disturbing factor such as the application of potential across the two electrodes immersed in the solution during the conductance measurement. However, when the potential is applied, the ions start moving towards the respective electrodes, and as a result of this, certain changes in the ionic atmosphere rise, which result in a decrease in the speeds of the ions. Debye-Huckel showed that these effects are due to two factors: A, the asymmetry effect, and B, the electrophoretic effect. The asymmetry relaxation effect arises from the fact that any central ion and its atmosphere are oppositively charged. Thus, when a potential is applied across the electrodes, the central ion and atmosphere tend to move in the opposite directions. The central positive ion will move towards cathode, while its atmosphere will tend to move towards anode. This results in the distortion of spherical symmetry, as is shown in the figure. The cation, the central ion, is experiencing a greater force behind it. Consequently, the force exerted by the atmosphere on the central ion is no longer uniform in all directions. It is greater behind the ion than in front of it. Electrophoretic effect. Ions in the medium are generally solvated, and when these move, they carry with them the associated solvent molecules. Any particular ion, say the central ion, does not move in a stationary medium, but through a medium in which the solvent molecules carried by the ions of the atmosphere move in the opposite direction. Electrophoretic effect continued. Similarly, the ions involved in the ionic atmosphere move in a medium of opposite moving solvent molecules carried by the central ion. Thus, both the types of ions, while moving in a solution, do not travel through a stationary medium but through a medium which moves in the opposite direction. These countercurrents make it more difficult for the ion to move through the solution and slow down its motion. This is known as electrophoretic effect. Debye-Huckel-Onsager equation. The magnitudes of these effects have been taken into consideration in the derivation of Onsager equation for a univalent electrolyte. The Onsager equation is lambda m is equal to lambda m infinity minus b lambda m infinity plus a under the root c, where a and b are Debye-Huckel-Onsager coefficients. The first term, b lambda m infinity, is the decrease in molar conductivity due to the asymmetry effect, and the second term, a under the root c, is due to the electrophoretic effect. Comparisons of the experimental data with the values predicted by Onsager equation reveals that the agreement is usually excellent in very dilute solutions up to about 0.02 moles per decimeter cube. In more concentrated solutions, the conductivity is usually higher than the value predicted from the Onsager equation. Now we have the experiment number 3 of conductance. The aim of this experiment is to determine the molar and equivalent conductivity, degree of dissociation and dissociation constant of 0.1 normal acetic acid at room temperature. We have already determined the molar and equivalent conductivity in experiment number 2. The materials required are conductivity meter, conductivity cell, 100 ml beaker, 100 ml measuring flask, pipette, acetic acid and conductivity water. Determine the equivalent conductivity at different concentrations of acetic acid already calculated in experiment number 2, and the equation lambda equivalent is equal to 1000 kappa by C can be used to find out the equivalent conductivity. According to equation B, which we have discussed earlier, 1 by lambda C is equal to 1 by lambda naught plus C lambda C by K equilibrium into lambda naught square. So, if we plot 1 by C against C lambda C, we will get a straight line and the slope and intercept can be calculated. The slope of the graph will be equal to 1 by K equilibrium into lambda naught square, and intercept is equal to 1 by lambda naught, and K equilibrium is equal to 1 by slope into lambda naught square, and Ka becomes equal to intercept whole square by slope. We also can calculate lambda naught from the literature values of the ions. For acetic acid, the lambda naught acetate ions and lambda naught H plus can be determined from the table, and then lambda naught can be calculated. Measure the conductance and equivalent conductivity using the formula K equilibrium is equal to C into lambda C by lambda naught whole square by 1 minus lambda C by lambda naught, and we can calculate the ionization constant of acetic acid using the literature values. Procedure: calculate the equivalent conductivity of the acetic acid solution as done in the experiment number 2. The molar and equivalent conductivities of acetic acid are equal. Plot the graph of 1 by lambda C on y-axis against C lambda C against x-axis. Extrapolate the graph to get the intercept. It is the value on the y-axis when C lambda C is equal to 0. Calculate lambda naught, and then we can tabulate our calculations according to this table, where for different concentrations of acetic acid, equivalent conductivity is tabulated, C lambda C is also tabulated, and 1 by lambda C is also calculated and tabulated. Find the slope of the graph and calculate Ka of acetic acid. Alpha, the degree of dissociation, can be calculated using the formula alpha is equal to under the root Ka by C for each concentration. So, after the Ka has been calculated from the graphical value, we can find out the value of alpha for different concentrations of acetic acid. So, room temperature is noted in degree centigrade. Alpha and Ka we have already determined. Another method in which we are using the lambda naught values to find out lambda naught acetic acid, which is equal to 390.7, and then again alpha can be calculated using lambda C is equal to alpha is equal to lambda C by lambda naught. So, now here we are calculating alpha from lambda C and lambda naught values, and then Ka can be calculated using the formula Ka is equal to C alpha square divided by 1 minus alpha for different concentration of acetic acid. The precautions to be taken are: use clean and dry beaker for each solution. Rinse and dry the conductivity cell before measuring the conductance of a solution. Dilution should be done accurately. So, let us take a break at this point. I will be continuing after the break.